Okay, thank you. I can speak to this microphone, it's fine. So, good afternoon. I'm going to talk about a method for the identification and characterization of vortices. And this method was inspired, motivated by a particular fluid dynamics problem. Can you hear me well? There's an echo. Is it okay? Yeah. Okay, so it was inspired by a particular fluid dynamics problem. So I'll introduce it first, describe this problem that we wanted to analyze, and then show the method and its application. So we were interested in the tip leakage flows in a high-pressure turbine of a jet engine. So if you consider a rotor and a turbine, and then there has to be a clearance above the tip of the blade, so between the blade and the casing of the engine to allow for the mutual motion. And a part of the flow isn't turned by the blade, but instead it is drawn into this gap due to the pressure difference. So it just crosses across the blade, across the tip, and then rolls up into this tip leakage vortex, and the vortex then dissipates. So this is what we call tip leakage flows, and they have a negative effect on the performance of the turbine because a part of the flow just goes through the gap. It isn't turned by the blade, so it doesn't do any work, and this leads to a loss of efficiency. So this is an important issue for the manufacturers of the turbines, of the jet engines, and they try to mitigate this effect somehow. One of the most common measures is to employ this tip geometry. So those are called squealer blades. And as you see here in the picture, they are formed by this rim that surrounds a cavity. So when the flow crosses across the blade through the tip gap, like here, it has to overcome two of these rims, and this helps to reduce the leakage mass flow. But of course, we could get more creative with the design of the tip. So we are not limited to this rim, but we could come up with more intricate designs, like for example this structure, or a smoothly curved surface of the tip. And there was a study at the Funkama Institute a couple of years ago that I was involved in, and they tried to do this, so to optimize the blade tip geometry to reduce the leakage mass flow and improve the efficiency of the jet engine. And there are some CFD simulations and did some experiments, and based on this they were able to determine which of the tip designs performs better, so which provides an improvement in efficiency. But the big question was, why does a particular design work? So how does it improve the behavior? How does it reduce the leakage of the flow? So to help to answer this question, we decided to analyze vortices, because the flow is driven by the tip leakage vortex and its evolution and dissipation, so it makes sense to have a look at the vortex structure. So we needed a method that would help us to identify the vortices and characterize them. And we had some requirements on the method. So we wanted it to be based on a sound definition, so that we would be able to distinguish, for example, vortices from the shear flows, which is, as we have had, a common problem in vortex detection. So that's the first point, that we wanted to have physically valid results. Then we wanted this method to be able to automatically perform a segmentation of the flow field, so to identify vortices as individual structures and to characterize each vortex by several parameters. So we have had that each approach to vortex identification has some pros and cons, so we can have region type methods and core line type methods, and we wanted to have the full picture of the vortex, so to identify the region as well as the core line. And an important point was that we just didn't want to look at the picture of the vortices, but we wanted to have some quantitative measure to be able to say that, for example, this blade design has by 5% stronger or weaker vortex than the other one. So we wanted to come up with some quantitative measure of vortex strength. So these are the requirements, and we didn't quite see any method at the time that would be able to give us what we needed. So we decided to develop our own methodology for the identification of and analysis of vortices. And as the basis of the method, we selected the triple decomposition of motion that was already described by Jakub. So, as we have already heard, the idea is that if we do the classical decomposition of velocity gradient into vorticity and strain rate, and then you use vorticity for vortex detection, our results, we have some false positives in shear flows. So vorticity is not a good quantity for detection of vortices. So almost 20 years ago, Václav Kolář had a very clever idea that he would perform a triple decomposition. So he would define a tensor that would represent the shear in the flow, and the residual tensor obtained by subtracting this pure shear tensor from velocity gradient. This residual tensor would be then decomposed into residual vorticity and residual strain. And this residual vorticity could then be used for the identification of vortices without this spurious shear component. This method has the advantages that the residual vorticity is a tensor of vector quantity, so we don't have just a value, but we also have the axis of rotation and the sense of rotation. And also the magnitude has some understandable physical meaning, so it is related to the rate of rotation of a rigid body. So how do we actually obtain residual vorticity? So this pure shear tensor was defined by Václav Kolář as a purely asymmetric tensor, and there are some examples how this tensor can look like. And we identify or we calculate this residual vorticity in 3 steps. So in the first one, we need to find a basic reference frame. So to make this decomposition unique, we have to perform it in a special reference frame. So that's the first step. Once we have it, this reference frame, then we subtract this pure shear tensor, obtain the residual tensor. And in the third step, we decompose this residual tensor into a symmetric and antisymmetric part. Where the antisymmetric part, finally, is our residual vorticity, which we then use for vortex identification. So one drawback of this procedure is that the first step to find this basic reference frame is quite costly. So there is no analytical formula in 3D. We have to use an iterative procedure. And this way, for each point in our flow domain, in this iterative manner, we find this basic reference frame. But once we have it, it is pretty straightforward. So then we applied this criterion in the traditional manner. So most of the methods for vortex identification are regional criteria that you set some value for a threshold and you draw an isosurface with this threshold value. So we compared our results with some traditional criteria. So nowadays I think that lambda 2 and Q and as well vorticity are the most used criteria for vortex identification. So we compared residual vorticity with those criteria. And we saw some consistency in the results. So all these methods captured some major vortices there, which is this lower passage vortex and the upper passage vortex. You can see them in all 4 pictures, as well as our tip leakage vortex, which we are most interested in. So those can be seen in the results of all 4 methods. But you can see the advantage of residual vorticity, that it really doesn't give these false positives in shear layers. So for all the other 3 criteria, you have this isosurface also along the walls, so on the blade, and along the up and casing of the machine. And with residual vorticity, we obtain a much clearer picture. But still, it isn't quite what we want, because we wanted to have those structures identified individually. And when you look at this result, we have basically 1 or maybe 2 or 3 surfaces that are wrapping around multiple structures, whereas we wanted to really identify each vortex as an individual structure. So we decided to perform some further processing of these results. So the input of the algorithm that we designed was this 3D field of residual vorticity. that we have just calculated. And the output would be a list of individual vortices. For each vortex, it would have its core line, its region extent, and also a measure of its strength. And we designed this algorithm, which has 3 steps. So in the first step, we identify the core line. And this is very similar to what was actually described in the previous speech. But we took a bit different approach. The definition of our core line is that it's the maximum line of residual vorticity. What does it mean? If you are at the core line and you construct a plane orthogonal to the local residual vorticity vector, then the maximum of residual vorticity magnitude in that plane should be at the core line point. So that's what you see here in the final step. And there are several ways how to obtain this maximum line, and we decided to use this predictor-corrector algorithm that was actually used already by Singh and Banks in 1994, but they used it for different fields, not for residual vorticity, of course. It wasn't invented by them. But the principal algorithm is quite useful, so that you start at a seed point, then you do a predictor step. So you predict the next point on your core line, and you take this step along the residual vorticity vector. Then, in the second step, you construct an orthogonal plane to the local residual vorticity vector, and your predicted point probably will not be exactly at the local maximum of the residual vorticity magnitude in that plane. So you do a correction in that plane to the maximum of residual vorticity. And this way you proceed along the core line. So the advantage of this algorithm is that you will not get a set of individual points which you don't have to connect, but you already have the core line as a feature, right? Because you are stepping along the core line. So in this way you are able to filter out some low quality structures and basically keep only the high quality structure, the vortices that are really relevant, without having some noisy results. And I also wanted to mention that this definition of this maximum line of residual vorticity can be also expressed using this parallel vector fields operator defined by Eichert and Roth in 1999, so that the criterion can be rephrased that you are looking for a set of points where the vector of residual vorticity is parallel to the gradient of residual vorticity magnitude. Right, so now we have our core line. So the next step is that we proceed along the core line, and for each point we construct a cross-section of the vortex. So to construct a cross-section, we construct a plane orthogonal to the local residual vorticity vector. And the main criterion how to determine the cross-section is that we define a threshold value of residual vorticity magnitude, and we just define the cross-section as an isoline. But we can impose some additional requirements to, again, filter out some low-quality features, so that, for example, you require that the angle between residual vorticity vector at the core and the residual vorticity vectors within the cross-section is below some threshold. So that, for example, we will not get the result that this point has a perpendicular residual vorticity vector than the point on the core line. So that's an additional criterion. But basically the main idea is that we will use this isoline. And once you have the cross-section, we can also calculate the strength of the vortex for this point. So we define this residual circulation. That means we just integrate residual vorticity magnitude within this cross-section. So for each point on our core line, now we have the cross-section as well as we have a value that describes its intensity. So that's the second major step of our algorithm. And in the final one, we have our cross-sections, and now we would like to construct a bounding surface for these cross-sections, so that we have the boundary of the vortex. And we can't just simply connect the cross-sections because some vortices that we identify can have multiple core lines within. So we took a different approach, and we just treat those cross-sections that we obtain as a cloud of points, and we try to wrap this cloud of points in a surface. If you do CFD, you may know this approach for the generation of meshes for faulty geometries. So if you have some CAD model with some missing faces, for example, or intersecting, some low-quality CAD model, you can use this shrink wrapping approach to create the surface that just wraps this geometry and then you generate your mesh. So this is a similar idea, and in the basic form, that you first create Cartesian mesh in the bounding box of your vortex, then you identify which of the cells contain at least one point from this cloud of points, and then you do some smoothing step. So as a result, you have this bounding surface that wraps around those cross sections. So now we have our core line, we have our cross sections, vortex strength, and the bounding surface. So it's time to apply our method to the test case and see what results we get. Here's the description of the test case. So it's quite a standard CFD simulation of this high pressure turbine stage. It is a steady state simulation using Rand's equations, and there's a mixing plane between the state and rotor. And we perform these simulations for all those different optimized tip geometries that we had. If you want to know more about the computational setup and some validation, I refer you to this paper from 2019, where it's described in detail. And here's a comparison of just using residual vorticity in the conventional manner, so just plotting an isosurface of some threshold value, and using this algorithm which identifies the individual vortices. So I think it's a much clearer picture. So you can really see the individual structures, identify these vortices along the rim, some vortices inside the cavity of the blade, and here this structure, it's the tip leakage vortex. And here we see resolved individually again, and the lower passage vortices and upper passage vortex and tip leakage vortex. So you get a much better insight into the structure, especially if you have many vortices there. So we use this method to analyze the over-tip flow structure for those different optimized geometries. And of course, we don't have the time now to go into detailed analysis of all these geometries, but I just wanted to show you that the over-tip flow structure can be very complicated. For example, in this case, we have tens of vortices in the over-tip region between the tip of the blade and the casing. So it's very useful to have this algorithm which identifies them individually and doesn't just draw an isosurface that would wrap all those structures. But still, I want to go in detail on one aspect of the analysis that we did. So there was one contradiction that we didn't quite understand in the results. And it concerns two of the blade tip designs. So one is this conventional simple square blade that has been used in the industry for the past 50 years. And the second one is an optimized design, this open rim square. So you see that there are openings in the front and rear part of the blade. Sorry. So we were surprised that actually the optimizer gave this type of design because there are these openings, so we have increased gap between the tip of the blade and the casing, which should result in larger mass flow, and that should lead to loss of efficiency. Right? We want to reduce our mass flow to zero ideally. And really, the tip leakage mass flow was increased by this design. But to our surprise, we saw that when we evaluated the efficiency, this design seemed as more efficient, even though the leakage mass flow was increased. So how was that possible? And this is where the quantitative analysis of vortices is very useful, where you can compare the strength of the vortex for those different designs. So we looked at the evolution of the tip leakage vortex. Here's a plot, so the red curve, that's the evolution of the vortex strength for the conventional simple skew blade. And this dashed black curve is the evolution of the strength for this optimized open skew design. And you see a clear difference here that for the combinational simple skew design, we have one peak of the vortex strength, so from the leading edge to the trailing edge, and then downstream, for the downstream, the vortex is dissipated. Whereas for the optimized open design, and you see the picture of the vortex structure here, you have this leakage jet of fluid through the opening in the aft part of the blade, right? So at this part, this is the opening, and a large mass of flow passes through this opening. And this jet then interacts with the tip leakage vortex. So it supplies additional momentum to the vortex, and this is why you see here the second peak in the intensity of the vortex for this optimized open design. So you have a first peak here, and then second peak here due to this leakage jet which supplies the momentum. And this has an interesting consequence because you see that the dissipation of this vortex occurs much further downstream. Right? So when you are here, the vortex of the simple skew blade has almost dissipated, whereas the vortex of this open skew is quite strong. So the dissipation is delayed. And you can see this also in the entropy evolution here. So if you are in a plane 50% of chord downstream of the blade, you see that the entropy, so this is graph of entropy, the entropy generated by the tip leakage vortex of the open rim blade is lower than the entropy generated by the simple skew design. Even though in the mixed out state, of course, naturally the entropy of the open rim design is higher because the leakage mass flow is higher. So eventually, the mixed out state, the entropy increase will be higher. But when we evaluate our efficiency, we have to do this between two planes. So we define one plane upstream and other plane downstream of the rotor. And in our case, the downstream plane was located here. And in this plane, the entropy generated by the tip leakage vortex of this open rim blade is lower because the dissipation is delayed. So this explains to us this seemingly contradiction because at this plane, the entropy of the open design is lower than the entropy of the simple skew. Even though in the mixed out state, eventually the open rim skew we have high entropy. So if we evaluated efficiency between this plane and the mixed out state, we would get different result. You would get the result that the open rim design is less efficient. So with this, I wanted to do a showcase of how plotting the strength of the vortices and be able to compare the case-to-case variations can be very useful in the analysis if we have this quantitative measure. So I'm coming to the conclusions. We have developed this method for the identification and analysis of vortices based on the residual vorticity. So residual vorticity was chosen because in our application it outperforms the traditional methods. It's able to distinguish between the actual swirling flow and shear flow. And it has some useful features for the identification of chord lines, that it's a vector quantity, and also it can give us a measure of the strength of the rotation in quite understandable and physically easy to explain manner. So we developed an algorithm which performed a segmentation of flow field. So automatically we would obtain this list of vortices, and for each vortex we would have the chord line and region and strength of the vortex. So if you want to see more about this method, I refer you to these papers which we published it's like 5 years ago in the Journal of Tube Machinery, these two papers, and there you can find detailed explanation of the algorithm and some results. And also I'm open to your questions.
Okay.